everyone, this is a presentation of the paper Speeding Up Word Inverse Distance and its variants via properties of distance between embeddings. My name is Matheus Werner and this work was done together with my advisor, Rel-RWMD. In this presentation, we will be talking about document distances. That's a crucial step for many applications such as document retrieval, task classification, and others. And it's important to remember that when we are talking about document distances, we are mainly talking about the representation, since the better the representation, the more trustworthy the results. Documents are usually represented as feature vectors using bag-of-words, LD, doc2vec, and others. And the distance between them is just the Kusner distance. And for this task, Kusner et al. Proposed a new distance using word embeddings called word inverse distance. The idea here is that each document is represented as its set of embeddings and weighted by its bag-of-word representation. And also the distance between two of these representations is given by the minimal cost of transforming one representation into the other, where this has to do with the Euclidean distance between their word embeddings. And formally, this can be modeled as a transportation problem on a complete bipartite graph, where in one side we have document 1 representing the supplies, and on the other side, document 2 representing the demands. And the cost of the edges between them is given by the Euclidean distance between the embeddings. And Kusner et al. Showed that this has very good results for their document classification task using KNNs. However, this takes super cubic time, so it's quite expensive. And also, it requires us to compute the distance between all the embeddings in these documents, or having a huge cache containing all the distance between embeddings of the vocabulary, which is usually impractical. And because of this, researchers proposed new ideas to improve this method. The first one to do this was Kusner himself. He proposed the relaxed word movers distance, or RWMD. This is the relaxation version of the WMD, such that the problem transforms into for each token in the document 1 finding the nearest one in the document 2. This decreases the complexity time from supercubic to quadratic. However, this is overshadowed by the fact that we have to first compute the distance between all the embeddings. And it's also important to notice that the RWMD presents results as good as the WMD. And continue in this line of work, Matheus et al. Proposed a linear implementation of the RWMD that is very good when we have to compare one document against many. The idea is to remove redundant computation of the distances, and to do so, what we have to do is to beforehand compute for each word in the vocabulary the closest one in the document, and then cache this information. So when we are computing the RWMD, what we will do is just to consult this cache instead of computing the minimum. And although these good results and improvement in the computational time, there are two main problems. The first one is that it is expensive initially to compute the distance between all the embeddings in the vocabulary against the document, and also it requires a any dimensional vector to cache all this information, which can be a problem when the number of documents is very large. And in this context, your approach is to speed up all the methods mentioned and also save up some cache. And the idea is very simple for doing this. If the relationship between words is more or less the same as the distance between the word embeddings, so if one word is related onto a few other words, the same should be expected from the embeddings. And so to see if this is really true, we compute the distance between one of the embeddings against all the vocabulary for one of our data sets. And as we can see, most of the distance stays between 1.2 and 1.4, with just some below 1.0. And the same behaviors seems to happen when we compare all the distance between all the embeddings. And so we propose two assumptions. The first one is that given the word W, the remaining words can be split into two groups. The first one are the related groups that consist of the R closest words to W, and the second one are the unrelated words to W that consist of the remaining words. And the second assumption is that the distance from every word in the unrelated group to word W is a same large vowel Cmax. And by using these assumptions, we can have two main benefits. The first one is that decrease the storage space for the cache from n squared to nr. And the second one that by focusing only on the related pairs, we can gain some speed up for the methods mentioned in the initial of this presentation, and we will show how to do this for the relaxed word movers distance. But first we have to see how to compute the cache, and this is very straightforward. We just have to compute the distance between all the word embeddings, and then for each word W, keep the R closest ones. And this can be quite expensive if the n of the vocabulary is large, and if so, one idea is to cluster the embeddings beforehand, and then just take the distance between the embeddings in the same cluster. And for modifying the relaxed movers distance, that in your case is named related to relaxed movers distance or Rel-RWMD, we have to modify a little bit the original cost function. The idea is that instead of the Euclidean distance, now is the Euclidean distance just if the word pairs is in cache, otherwise is the val Cmax. And then if we store each document as a hash table, what we can do is instead of for each token computing the closest one in the other document, we can for each word access its related words that are the main ones, and just check if any of them is in the other document, and the ones that are, we take the minimum, and so this decreases the cost from quadratic to dr, where r is a small vowel. And for the linear one, it still continues to be linear. However, the initial cost to compute the distance between all the embedded to the document, there is not more necessity for this. We can just take the R closest ones to the words in that document, and also the cache space required decreases to dr. And to see how we go in practice with your approach, we propose two experiments. And the first one is the document classification via KNNs. We will see this experiment in two aspects. The first one is the quality of the results, and the second one is the runtime. And we'll be comparing our results against the Kusner, the WMD, and the RWMD. It is important to note that before running this experiment, you have to select a vowel for R. What we do is that we run a cross-validation between some possible R's, and then take the best one for a validation set. And as we can see in this table, the Kusner one is the worst, what's expected, and between the others they are more or less the same. And in question of the running times, the Kusner is the faster, the WMD is the slowest, what are expected. And between the remaining versions, yours is the fastest by 1 order of magnitude. And we implemented the linear version because we are comparing many documents. However, we are not being fair in this comparison because we are not taking into consideration the time for the cross-validation. And to see if this step is really necessary, we run the same experiment between two strategies. One is using cross-validation and the other is running a fixed R. And as we can see, if a fixed R equals 16, we have results as good as the cross-validation. And well, for the second experiment, we run the identify related documents. The idea is that we have 3 documents, and 2 of them are related. And as we can see, once again, your method has closing results to the WMD and RWMD, however, being 1 order of magnitude faster once again. So the conclusion is that the distance between the most of the embeddings are irrelevant, and that if we focus only the important word pairs, we can save up some cache, and also speed up all the methods mentioned, while also maintain the same level of quality. Thank you.